All right, so today should be a pretty relatively quick lesson because obviously we're on day 2, so that means we have to finish up this unit and take your test. So obviously this lesson is going to be a little bit shorter because then the remainder of this time is for you to be working on your quizzes and your tests here. All right, so again, if I share my screen with you, what I mean is yesterday we talked about 5.1 and 5.2, right? So we introduced the law of sine and the law of cosines. And then today we're going to work on 5.3, which is vectors. We will review a little bit for 5.4 to wrap it all up here. But then once we're done with both of those, we're going to stop because obviously you have this one quiz here. You have an extra credit opportunity for practice. You have an extra credit discussion opportunity, and then of course you have to take your CST. And since these tests take longer than quizzes, I want to make sure that I give you some time to do that. So that is our plan for today. Again, remember, we are nearing the end of this here, so please make sure that if you're not caught up, you're trying your hardest to get caught up in these last few days here. All right, so, all right, so going to 5.3 here, if we're looking at vectors, all right, so in math and in physics, which luckily you guys are going to be taking here this coming year, you're going to learn about this thing called vectors, all right, and what you can do is vectors are basically quantities that have a direction. Okay, they're quantities that have a direction. All right, again, height and age are obviously easy things that can be represented by a number, but some things are a little bit more difficult. For example, if you are walking northeast at 2 feet per second, okay, so it's talking about speed and direction being two things, all right, and one of those ways that we can describe this is using, of course, vectors, because like I said, vectors are a number and a magnitude, or I'm sorry, they're a magnitude and a direction, right? So they have that number and they have a way of which they're going, okay? So we're going to talk about vectors, and of course you'll use this more in physics, and you'll have hopefully a little bit of leg up on those people who have never seen this before here. All right, so looking at the introductory video here, they want to talk about a model airplane. Okay, so looking at it, a model airplane is flying north at 20 miles per hour. Obviously, there's a headwind and a tailwind. We'll either slow it down or speed it up. Now, suppose that there's a wind blowing from the west at 20 miles per hour. It's not too hard to see that the path of the plane would look like this, although the speedometer is saying the plane is going 20 miles per hour. Okay, so then it's asking you, what's the actual ground speed? And then finally, if that wind is slightly changed, okay, we can see the trajectory is changed here, but what would the plane be going at, right? So how does that affect our plane? All right, and again, the reason that is because when it's blowing that wind, it's blowing it off course, but a speedometer can only tell you how far you're going, right? And take it outside of an airplane, right? If you're driving in your car, okay, you can be going 55 miles an hour down the highway, right? A straight shot down the highway. Or you could be going 55 miles an hour on a curved part, right? And your pathways are going to look very different, even though the speedometer says that you're still going 55 miles per hour. Okay, so we're going to look at how do we describe those? What do they look like? All these different things. And again, it's all under the guise of this term, this new term here called a vector. All right, a vector. All right, so again, a vector is an amount or a magnitude along with a direction. All right. So again, this first example here said it was going straight at 20 miles per hour, flying north at 20 miles per hour. So again, hopefully you know, never eat slimy worms or whatever, north, east, south, west. All right. So again, we know the plane is flying north and we know it's going at 20 miles per hour. So since we know the magnitude and the direction, we can represent this with a vector. All right, so it is a vector. And what this vector is it's a straight line with an arrow. Okay, it's a straight line with an arrow, and that arrow indicates our direction. All right, it indicates our direction. And if we read this formal definition here, a vector can be represented by a line segment indicating the length of the magnitude of the vector and an arrow specifying directions. Okay, a length of the magnitude and the arrow tells you the direction. Okay, so then if we go to our XY coordinate plane, right, we can represent vectors there as well. All right, and we can represent vectors, it's saying centered at the origin. Okay, the arrow points in the vector's direction and the length of the arrow is the vector's magnitude. All right, so again, back to that plane example here, if each one of those little dashed lines stood for 1, then we would go up north because we were talking about north, and we would go up 20 dashes, right, indicating our length is 20, meaning that's our value. Okay, and since any vector in the plane starts at the origin, it's uniquely determined by the coordinate of its tip. All right, so again, the tip of the arrow. All right, because all vectors in the XY coordinate, we're going to say start at our origin to make it simple here. It's going to start at our origin. All right, and then also if we have something not perfectly horizontal or vertical, we can use our Pythagorean theorem or our distance formula in order to calculate our magnitude, right? Since we're starting at our origin here. Okay. So again, they're usually denoted, and it's saying boldface. Oh, apologies. All right, usually denoted in boldface. So this is called a vector bolded V. All right. Each tick represents one unit, right? And the coordinate form of this vector is given by just the last point there. Remember, because all of them are going to start at the origin, we just ignore that, and so we indicate this vector here as its point 4, 2. Again, 4 because it's 4 in the X direction, 2 in the Y direction. All right, 4, 2. And we can then calculate the magnitude of this by turning this into our right triangle. We can either use Pythagorean theorem or we can use our distance formula, whatever you would like. But regardless, we know that V squared is going to be equal to 4 squared plus 2 squared. We take the square root and that gives us our magnitude here. All right, and obviously we could leave it as square root of 20. We could plug square root of 20 into our calculator and actually get a value out. Or another way of simplifying, remember, is if we have a square root here, we can separate this out into its factors. So 20, we can get 20 by doing 4 times 5, right? And if we take the square root of 4, that gives us 2. So that's how we get this 2 square root of 5 here instead of square root of 20. Okay. So then here it's asking you, what are the coordinates of the vector W? So if we're looking here, 1, 2, 3, 4. So we're at -3, 4. All right. What is the magnitude of W? All right. What is the magnitude? So this is saying A squared plus B squared equals C squared. All right. And the answer to that is 5, because remember, -3 squared gives us 9. Plus 4 squared, which is 16, that gives us 25. We take the square root of 25, we get out our answer of 5 here. Okay, we get out our answer of 5. All right, so then how do you read this right here? What this is saying is let bolded V means vector equal 5, -15. All right, so that's saying, again, it's starting at the origin. We're going over 5 and down 15. All right, we're going over 5 and down 15. All right, and to look at the math here, when it's saying those bars, that absolute value of V, this is asking you for the magnitude, right? What is the magnitude of this vector here? All right, what is the magnitude of this vector? All right, and so again, all you have to do without even seeing it on a graph here is you just use your Pythagorean theorem. All right, you use your Pythagorean theorem. And since it says round your answer to 2 decimal places, that means you know you're going to have to calculate it, right? So instead of leaving it as square root of 275, we're going to have to actually plug this into your calculator and get your 16.55. All right. So then, of course, which of the following represents this graph here? Well, it's going to be over 7, right? Because that's saying over 7 down 15. So you're going to be looking at graph D here, okay? So either knowing what to do with these points, or you can always draw a graph and then solve from there, okay? Hopefully not too terribly difficult. All right, so then if we summarize this here, again, remember, bolded V stands for vector, all right? And we indicate what the vector is by its XY coordinate, right? And that XY coordinate tells us where the vector is ending, where the tip of that arrow goes, right? Because all vectors start at our origin of 0, 0. All right, again, the values X and Y are the coordinates of the vector, and it's obviously on our XY plane here. All right, and the magnitude or the length of our vector is written as this absolute value of bolded V, okay? And what that's asking you is just the distance or the length of that line, okay? So we can use Pythagorean theorem or our distance formula, and we end up with the square root of x squared plus y squared will give us our magnitude of our V here. Okay, and again, regardless of if whatever quadrant we're in, when we're doing our magnitude here, we're just talking about an absolute distance, which is why it has that absolute value bar. Okay, so all of your values are going to be positive there. Okay, it's going to be positive. Sorry, and then looking more specifically here, okay, a common quantity that we denote by using a vector is velocity. Okay, so how fast is something going and what direction is it moving in, right? So how fast is something going and what direction is it moving in? All right, and of course, a lot of these we're going to talk about is like speeds and cars and trains and all of that kind of stuff. Okay, but the difference here between velocity and speed, okay, the velocity and speed is that speed is how fast an object is going, all right, but velocity takes into effect how fast it's going and what direction it's moving in, okay? So speed is the magnitude of a velocity vector. Okay, speed is the is the magnitude of our velocity vector. Okay, because of course velocity takes into account how fast we're going and where we're going. All right. So then if we look here to move forward, let me just double check here. Yep, perfect. Okay, so to move forward here, okay, we talked about that plane. It was moving north at 20 miles per hour, okay, except for there was another wind. Okay, there was a wind, and it also had a vector, right? So wind obviously was going to take some effect on the airplane there, all right? And so what we're going to do is, in order to see the effect that the vector of our wind has, it's going to be added to it. It's going to be added to it. So it's really, really kind of an easy concept. You literally just add the two vectors together. You add the coordinates. So if we have our original vector, vector 1, V1, okay, and we have a second vector that has an effect on it, V2, we just add them together. All right, so literally you take x1, y1 plus x2, y2. and our new coordinates become whatever x1 plus x2 is, whatever y1 plus y2 is. So if we look down here, again, our plane was flying north, so straight up at 20 miles per hour, okay? This on our vector plane would be 0, 20, okay? 0 because we're going straight north, all right? Magnitude being 20, obviously, because we're going 20 miles per hour. All right. So that's what it would look like on our graph. Okay, that's what it would look like on our graph. Now, we have the wind that's blowing west, so directly west. All right. At 20, or sorry, it's blowing from the west at 20 miles per hour. So it's blowing from the west. So it starts here and it's going this way. All right. At a magnitude of 20. So of course, if it's directly blowing from the west, it's going to be on our x-axis. All right. And so the magnitude of this becomes now 20, 0, because we go 20 over, but there's no effect on our y coordinate here. Okay. So when we look to see the path of our new airplane, we just add them together here. We have our new vector v is the vector of the plane plus the vector of the wind. So we literally just add them together, right? So we have our xy of our plane, our xy of our wind, and what we can do here is we can combine our x values and combine our y values. And for both of them, it ends up with a 20 and a 0. So our new path of our airplane becomes 2020 here, right? It becomes 2020 here. All right, that is our new velocity. All right, that is our new velocity. Now, it's asking, what is the speed of the airplane? Okay, so we figured out our velocity is 2020. Now, remember, our magnitude here is our speed. Our magnitude is our speed. So what we're going to have to do is we're going to have to figure out the magnitude of this line here. Okay, we're going to have to figure out the magnitude of this line. And all we have to do is take our a squared plus b squared and take the square root of it. And once we do that, we get a speed of about 28.28. Okay, so it's clear that the plane is going faster than its original 20 miles per hour, but it is also going off course at an angle here. All right, at an angle here. All right, and we could measure the angle, or you could know that halfway between 0 and 90 is 45. So clearly this plane has gone off angle at 45 degrees based on our wind here. Okay, now if the wind is blowing east at 10 miles per hour, all right, all we do here is we just shorten our wind vector, right? So our wind vector is at 10, 0. And again, we just add them together. So we get a vector at 10, 20, right? We get a vector at 10, 20 because we just added them straight together here. All right. In order to do our speed, okay, in order to do our speed, we're going to take the square root of our a squared plus our b squared here, right? So 10 squared plus 20 squared, we're left with approximately 22.36. All right, we're left with approximately 22 degrees. All right. And what we can do here is what angle away from the horizon. We can use one of our inverse trig functions, right? We can use one of our inverse trig functions to figure out what degree we have here. So let me just type in a 1. Okay, so if we do this, we can use our inverse trig function. And for this one, I would use the values that were already given, not something you had to calculate. So because of this, we could use our inverse tan function. All right, and and we can get this, again, using our calculator and our inverse tan function. So tan to the -1, we can get it to be about 1.11 radians. All right, which is equal to about 63.6 degrees. All right. So our plane is traveled off course, and we can see that it's traveled off course by, originally it was supposed to be 90, right? And it's gone off this far. And this angle here is our 63 degrees. So we go 90 minus 63. And so we know that this angle here, between where we wanted to go and between where we're going now, is now 26 degrees. Okay, so we can say we're 26 degrees off course and we're going at a speed of about 22 miles per hour. Okay, so looking at vectors again here, we can do a subtraction here. We can also do a subtraction here. And it follows the same exact process here. You just take V1 minus V2. So you subtract the X coordinates from each other and you subtract the Y coordinates of each other. All right. And that would be if you're looking for the difference between two vectors. If you're looking for the difference between two vectors. All right. And then vectors can also be scalar, which means we can multiply them up, right? And the scalar constant can be any real number, all right? So, for example, if we have our plane and we say, okay, well, we want to scale that up by a factor of 3, you would just have a 3 out in front and you multiply both your X and your Y coordinates by whatever that value is out front, okay? So this is called our scalar multiplication because we're multiplying everything by a factor in order to scale something up or scale something down, right? We can scale something down as well if we multiply by something less than 1, okay? So if we watch this here, we've got our V1 and our V2 that are our red vectors, and if we add them together, we get that blue vector there, okay? And it's saying, geometrically, the sum is the diagonal of the parallelogram determined by the two given vectors. All right. So basically, you're adding them together, right? You're adding them together. And if you notice here, this red one, this bottom red one here is the same length as this top, and this shorter one here goes there, right? So that's all it's saying here. And sometimes this is referred to as the head to tail addition method. Since you can imagine, there we go, moving. You can imagine moving them on top of each other, all right? You can also add the vectors to get a different vector, right? And again, if we were to do, oh, it going really quickly here. If we were to do a head to tail method, what we would do is, again, we could take that bottom part and move it to the top, right? So there's a lot of different ways of looking at this here. If we have, again, our same two vectors here, and we want to take the difference, okay? We want to take the difference between them. It's all we do is we subtract them, okay? So it would be, we would subtract them if we knew the actual coordinates, and it would give us these values here, all right? Or another way of determining the difference here is the line between them, right? The line that connects them. All right, so it's the line segment that connects our V2 to our V1. All right, again, it's an application of this head to tail method. All right, but again, if this is confusing you, you'll work more with this in physics, so you can stick to the algebraic understanding if you'd like. All right, but basically know that when you're taking the addition, right, you take one of them and move it on top of the other, right, in the same exact direction. You don't change, you don't flip, nothing. You just take it and you add it on top. All right, when you're taking the difference, you're trying to connect both of them, and what you connect them, right, that line, you then bring it back to the origin, same magnitude, same direction, it becomes your difference. Okay. So same thing here, right? The difference between the two vectors, you move it back to the origin, and there you go. Okay, now looking at scalar multiplication here, okay? Again, it started off as a smaller one, all right, and then it's saying, I want 2 times that, right? So you multiply both coordinates by 2, all right? If we look at 2/3, we can also do, we can also do 2/3 of something, right? So we can make it less than the original value. And here they're saying is if you multiply it by 0, okay? And if you multiply it by 0, obviously it gets to the origin there. So you can't multiply by 0. So it has to be greater than or less than our value of 0. And if we multiply by something less than 0, okay, we can get negative directions here. Okay, so again, that could be a scalar in the negative direction. All right. Then moving forward here, we can use scalar multiplication to find our unit vector. Okay, so we can use scalar multiplication to find our unit vector. And if we look at what the definition of our unit vector is, it's just a vector with a magnitude of 1. All right, again, trying to relate it to our vectors, or I'm sorry, our unit circle, right? So if it has a magnitude of 1, it's getting similar to our unit circle, which has a radius of 1. Hence why we call it a unit vector. Okay, so if we let our vector be a non-zero vector, right, our non-zero vector, the unit vector associated has a magnitude of 1, all right, and it's the same direction as our vector, all right, and hopefully not too terribly difficult. We're just trying to relate our normal vectors onto our unit circle here, okay, onto our unit circle, all right. And again, since it has a multitude of 1, it's just a scalar multitude of our vector. All right, it's just our vector here. Okay. Every direction has a unique unit vector, right? As we would think, it has a unique unit vector here. So this is where it's a little bit different than our unit circle, because in our unit circle, right, we had some of the points being similar here. But now when we're dealing with vectors, we're dealing with an x and a y coordinate. We're dealing with an x and a y coordinate. So all of these are going to be different because they're in obviously different quadrants. So even though they might have the same absolute numbers for the x and the y coordinates, right, it's going to have different magnitudes because it's negative or positive. Okay. And then what we can do is we can combine vector addition and scalar multiplication to form linear combinations of our vectors here. All right, so if we have 2 different vectors, vector v and vector w, all right, and c and d are 2 scalars, so they're 2 different scales, all right, then we can have a combination in this kind of form here. So basically, what this is saying is you just plug it in and you do order of operations. Okay, so if we're looking at vector v and vector w in the linear combination of 3v plus 2w, okay? So first off, you replace v and w with the coordinates, right? You replace v and w with its coordinates. All right, then based on order of operations, we're gonna multiply out our 3 and our 2 through those coordinates that are there. Then finally, we combine our x coordinates and our y coordinates, all right, to get our new linear combination from our vector, all right? So again, hopefully not too terribly difficult, just knowing that you have to replace and then follow order of operations, okay? And I will let you guys look at this practice here, all right? All right, and you can actually try this out on your own here. But basically, this is asking you to do scalar products, all right? So hopefully not too terribly difficult, and you can see the reasons as to why. But basically, all you're doing is taking that constant and multiplying it by both factors. So 2 times 6, 2 times -4. Half times 6, half times -4. All right? Then what this is asking you is, what is the missing vertex on the parallelogram in the diagram below? Okay, so we have a vertex here and we have a vertex here. All right. So what is the vertex that we are clearly missing here? And if you look, it's going to be the one that connects them in the middle here. All right. It's going to connect them in the middle because this is talking about the sum. All right. This is talking about our sum of our vectors. So originally what this is saying is remember, we start at our origin. Okay. Our vectors always start at our origin. So we go origin up to this coordinate here. Okay. And we have our origin down to this coordinate here. All right. And these two red ones here are showing the connection. It's showing the connection between the two of them, right? It's showing the connection between the two of them. And showing a connection between is talking about addition, right? It's talking about addition, adding these two together. Right? And again, you can see if you did that head to toe method or head to tail method, it basically, I grabbed this entire vector here and I moved it to the end of this first vector, and that's how I got here. Same thing, I grabbed this vector, moved it to the end of this one. All right, so regardless though, this shows our additive. All right, so what we needed here was a vector that would get right here. All right, and again, how did we get those specific numbers? All we did was we took our x coordinates, added them together, took our y coordinates, added them together. All right, and then it's asking you for the magnitude of this answer here. So again, all you would do is a squared minus b squared, or sorry, a squared plus b squared, take the square root of it. Okay, take the square root of it. All right, and then finally for this last one here, the linear combination. Okay, what you need to do is you need to, again, follow the order of operations. So carry out your multiplication first, then you add your x coordinates and your y coordinates. All right, so carry out your multiplication first, then add your coordinates. Same thing here, right? You carry that negative sign out and carry this -6, and then you add your like components. All right, and I'll let you try the rest of these for your linear combinations here. Okay, so again, we've introduced a lot of new things here, so hopefully it's not too terribly difficult. Okay, again, it's a new way of thinking, but the actual mathematical properties are very, very simple, right? Like just adding and multiplying and distribution. So it shouldn't be mathematically difficult. It should just be a little bit of maybe new understanding here. Okay. And something that's going to be very new to a lot of us is this thing called a dot product. Okay, it's called a dot product. All right, and what it is it multiplies two vectors together. Okay, so it's called a dot product because you have v1 dot v2, right? Meaning the dot is a multiplication. All right, so the equation for this here is I take x1 times by x2 plus y1 times by y2. All right, and so our dot product is not written, it is not written as an xy coordinate. Okay, it's only written as one answer. All right, so for example here, if we had the coordinates 2, 1, dot 3, 6, right? So this is vector 1 dot vector 2. We multiply our x components, we multiply our y components, and then we add them together, right? Or subtract in this case because we had a -1 there. All right, but when we did this, we get to a value of 2 here. Okay. And then of course, what would any rule be without some special cases here? All right, so of course, if we have the same vector being multiplied by itself, right? V times by V, it's just going to give you x squared plus y squared. All right, you still have to add them together to get that one value, but it just gives you this x squared plus y squared. All right, and thus we can relate this by also saying the absolute value of v squared. All right, we could also say the absolute value of r v squared. okay? And then of course we've been talking a lot about trig, so we got to bring it back there. How do we figure out the angle between our two vectors? Okay, how do we figure out this angle between our two vectors? All right, and luckily we have an equation that solves this for us. All right, but again, assuming v1 is at x1, y1, and v2 is at x2, y2. Okay, what we can say here is if we use this dot product, okay, if we use this dot product, we can say v1 dot v2 is equal to the absolute value of v1 times by the absolute value of v2 times by cosine of theta. Okay, times by cosine of theta. So of course we do a little bit of algebraic magic here. We reassign, or sorry, we redistribute this equation. Okay, and we're left with cosine of theta is equal to v1 dot v2 over v1, absolute value of v1 multiplied by the absolute value of v2. Okay, so if we look here, we can go through that a little bit more in detail here. All right, so we look at our two vectors, okay, vector 1, vector 2. All right, if we do the dot product, again, pause. If we do the dot product, all right, it gives us x times x plus y times y. All right, and that gives us this value of 0 here. Okay, then if we look at the magnitude, right, that's what it's saying. So the absolute value bars here, when we're talking about vectors, are talking about our magnitude. All right, so when we're looking at this, we're looking for the length, right, the length of those lines here. All right, so our magnitude for v1, again, is the square root of b squared plus a squared, right, and that gives us the square root of 18. And this magnitude here for our second vector gives us square root of 2. Okay, gives us this square root of 2. All right, so then if we were to compute the entire dot product, okay, we were to compute this entire dot product here. All right, we would have our v1 dot v2 is equal to our absolute value, or our magnitude of v1 times by magnitude of v2 cosine theta. All right, cosine theta. Okay, and here what they do is they plug in for our cosine of theta being pi over 2. All right, and since it's pi over 2, it gives us this 0 value, and that's equal to 0. Okay, that's equal to our 0 here. All right, if we look at a couple others, okay, so looking at these, again, we calculate the dot product directly. We calculate the magnitude of each of those vectors. We have our equation, and we plug it into our original equation here. Okay, we can plug it into our original equation here. And I wish they would have wrote this differently here, okay? They're saying compute the dot product using the angle formula given, okay? Well, that would be talking about this guy here. However, we don't know what theta is in a lot of these cases. So you would actually have to use this guy here to figure out what your cosine is, right? To figure out what your cosine is. Since we technically know what our dot product is, so we know what this left-hand side is, we know what both of those magnitudes are, what we don't know is our cosine of theta. All right, and what they're doing here is they're trying to show you that if we were to know that this is pi over 4, if we were to know this and we plugged it in directly into this equation, we would calculate out a value of 1, and that would also be what we equaled here if we calculated it directly, okay? So I'm not expecting you to know that this was pi over 4, the last one was pi over 2 right off the bat. That would have to be something either told to you, or you would use this equation, right, this different form of the equation in order to figure out what the angle actually is, okay? Right, so perfect. This is exactly it, right? You'd have to figure out what the angle actually is here. So again, you would just use that modified version, and once you got your right-hand answer, -8/17, you would do the inverse cosine, right? Inverse cosine would give you one answer in radians. You can convert that to degrees, and then we're left with 118 degrees, or sorry, 118.07 degrees, okay? So again, knowing what you have and what equation you can use there. All right. So then we can do this thing called orthogonality, right? Or orthogonal, also meaning perpendicular. All right. The formal definition, if you forget what perpendicular is that the angle between them is 90 degrees, or they form together to make a right angle. Okay. Or you could also say a T shape. All right. So orthogonal means it gives you a right. It gives you a 90-degree angle. Okay. So one way we can test for that. One result of the dot product is that it could give us a way to test if they are perpendicular. All right. If they are perpendicular. And the way that we'll know that they're perpendicular is that if we do the dot product, we multiply them together and we get a 0. Okay, if we do that, we know that they are perpendicular to each other. So the angle between them will be 90 degrees, right? So these guys here, right? So for number 2, when they did the math, the dot product, negative 60 plus 60, that equals 0. All right, so this one is orthogonal. Up here, the value ends up being 14, which is not equal to 0. Therefore, they're not orthogonal to each other or perpendicular. All right. So it's just a quick little shortcut way of figuring out if they're right 90 degrees away from each other. Okay. Additionally, we can write any vector as a sum of 2 perpendicular vectors. All right, so for example here, instead of saying x, y, we could say x comma 0 plus y comma 0, right? And the reason that is because if we add these together, it would be x plus 0, y plus 0, which is just x comma y, all right? And for this example here, right, for this example here, we could have it also simplified further, right? We could pull out an x coordinate and a y coordinate from both of these factors, right? So if we pull an x out of x, we get a 1, and if we pull an x out of 0, we still get 0. Same thing here. So we can simplify our vector, right? We can split it up into 2 sums, right? The sum of 2 terms, and we can even pull our x and our y coordinate out of those terms to simplify it even further. Okay, because it gives us these 2 vectors, 1, 0 and 0, 1. So we have 1, 0, 0, 1. And these are called our standard base vectors. Okay, they're our standard base vectors. Okay, and so what we can do then is we can use these as kind of guiding points here. And so any vector can be written as a sum of the components based on our base vectors here. All right. So the coefficients x and y would be the coordinates of our vector v. All right. So for example here, if we have -2, 5, it's like saying -2 E1 plus 5 of E2. Again, because E1 is our original vector here talking about our x direction, and E2 is talking about our y direction. So we went -2 in the x direction and +5 in the y. All right. And the reason we can do this here is because it makes it easier for us to look at our vector components and our angles. All right. So dealing with things in terms of E1 and E2 become easier because then we can then use them like XY coordinates. Okay, we can use them like XY coordinates. So for example here, if we look at a vector with a magnitude of 12 at 49 degrees, so 12 at 49 degrees here. All right, our x and our y coordinates, right, are based on cosine and sine, just normal trig functions here, right, that we've talked about. So it's 12 cosine of 49 and 12 sine of 49. Again, depending on x and y. Okay, so the magnitude of the vector 12, again, lies on the circle of radius centered at the origin. All right, so our x component is, of course, 12 cosine 49, but we say E1, right? E1. Because remember, that's saying that we have this in the x direction, but we don't have it in the y direction, right? So that would be saying this line here is this first component, all right? Plus a line that goes up this way, right? That's what this second part is saying, up this way. So it's saying if I add a line that went here and a line that went here, that's how I get to this final component, right? That's how I get to this final component, right? And of course, then it can get simplified down to just our x and our y coordinates without our E1 and E2 for our vector, okay? Without our E1 and our E2 for a vector. So in general, if a vector has a magnitude and an angle, we can write our vector as magnitude times by cosine of theta, comma, magnitude sine of theta, right? So magnitude being 12 cosine theta, 12 sine theta, right? Again, very similar to the stuff we worked with for unit circles. All right, and then another property of dot product is this thing called projection, okay? This thing called projection. So if we have two vectors that are non-zero, okay, are non-zero. And we're going to look at what happens if they are orthogonal or not orthogonal. All right, so again, if these two vectors are orthogonal or they make a right angle, okay, they make a right angle, you could say that V1 does not point in the direction of V1 at all. Okay, you could say that it does not point in the direction, I think it's supposed to say of V2 at all, right? So V1 is going, let's go straight up and down. V2 is going left and right. So they don't point in the direction at all, okay? But here, if they're not orthogonal, if they don't make a right triangle, or sorry, a 90-degree angle, okay? You can ask how much of V1's magnitude points in the direction of V2. All right, so looking at this here, apparently this one's going to talk here. All right, we're going to notice if they're not at a 90-degree angle, we can talk about how much one points in the direction of the other.
As the components of a given vector V is to imagine, one way to visualize the components of a given vector V is to imagine the shadow that the vector casts onto each coordinate axis.
Okay, so again, remembering that this is a reflection of E1 and this is a reflection of E2. All right, so we have this X E1, Y V2, or sorry, Y E2.
Now try the same thing, except in this case, project V onto W. The length of the shadow of V on W is determined by the perpendicular line drawn from the tip of V onto W. How can you find the length P?
Okay, so looking at length P here, obviously this is a right-hand triangle that we can make between them. And so if we do this here, we can then just use our trig function. And for this example here, we're going to use cosine, right? We're going to use cosine. And again, this absolute value of V is standing for the magnitude, right? So that linear blue line right there. So we can rearrange this. And what we can do here is first we can solve for our cosine, right? We can use our cosine angle there, and we can get our dot products that we're more familiar with here. All right, and if we can get this here, right, this statement, and we also know that this top statement is true based on trig functions, right? If we know that these two are both true, we can set them equal to each other. So then our expression here, we just replace cosine theta in this top expression. We just replaced cosine theta in this top expression, and it gives us this new equation here where we have P is equal to the dot product of V times W over the magnitude of W. All right. Perfect. All right. And then since P is scalar, the quantity is called the scalar projection. All right. It denotes the shadow of V onto W. All right. It's the shadow of V onto W. All right. So again, if we take two vectors here, we can calculate the scalar projection using this new formula that we learned here. So we take our projection, right? We draw a straight line down, and we're gonna ask, what is this length here? So what is this length here? All right, and what we can do, of course, is take, again, the dot product of V and W, so V and W over the magnitude of W, right? Over the magnitude of W here. So we can calculate out our scalar projection. All right, and a practice problem here that you can try when you're doing that. Okay, and I know this was a lot of information, so let's take a minute here and just make some final conclusions here. All right, so V and W are two different vectors, and again, you can know that they're vectors because they're bolded, right? They're bolded. That's one of the key things there. All right, and so if we're looking at the scalar projection of V onto W, again, V onto W, okay, how much of vector V is reflected on W? All right, you can use this equation here. All right, you can use this equation here. All right, and the projection of V onto W is a scalar projection multiplied by the unit vector in the direction of W. Okay, so again, it's dictated, what this is showing you here is it's dictated by the by the direction of W here. If this was closer to V, right, it would be more of V reflected on it. If it was farther away, there would be less of it reflected, right? So that's all it's saying for that second value there. Okay, and then of course, there's a lot of practice problems for you to try in terms of magnitude, scalar projections, looking at things if they're orthogonal or not, right? And then obviously solving for the angle between two given vectors. So again, making sure that you really take some time to go through that is going to be important. All right, and then of course, we're going to summarize this here with our study guide. Again, a vector is an amount or a magnitude together with a direction. So it is a value and a direction. All right. The coordinates for the different vectors, again, we just write them as XY coordinates. If we're talking about a vector by itself, and again, that coordinate is where the tip of the arrow is. So it always starts at your origin and your arrow goes out from there. All right. So the magnitude of the vector is talking about the length of this, and we always have it as a positive value because it is a distance, right? So we're talking about the magnitude, we're just talking about the total distance, not the distance plus the direction. All right, and then of course the magnitude is the speed, right? So the magnitude here is the speed of the object. All right, it's the speed of a velocity vector. Okay, and then we talked about if you wanted to calculate just the magnitude, you use your Pythagorean theorem. If you want to calculate two things added together, right, if something's affecting the other, you just take the sum of them, right? You add the x components, you add the y components. All right, you add the x and you add the y components. So then here for this guy, it's saying using the head to tail method. So what this is asking you to do is take vector 1 and draw it on top of vector 2. So if you notice here, vector 1 goes over 1, 2, 3, 4, 5, 6. So it goes over 6 and up 1, 2, 3. Okay, so what you would do here is you would go again over 6. So 1, 2, 3, 4, 5, 6, up 3, 1, 2, 3. So you would mark that point and you would draw a line to that point. And that's exactly what they did here. They draw it to that point. And then you do the opposite for V2, right? So V2 goes over 2, up 7. So you go to V1, over 2, up 7. And essentially, if you do it correct, they should both bring you to the same point, right? And that ending point is now the ending point for your new summative vector. Okay, so that would be how you do this head to tail method. All right, so same thing with smaller guys here. Again, knowing how many over, how many up. That's all it's asking you to do. All right. Scalar multiplication, all right, that's just asking you to multiply by whatever the constant out in front is, and it can be less than 1, it can be a negative value even, right? And this one here is just saying multiply by 3. So you're going to repeat this 3 times, right? So including this is 1, you'll do it again 2, you'll do it again 3, all right? And if you notice here, this is over 3, up 1. Okay, so you're doing this on multiples of over 3, up 1. So if we do it again, over 1, 2, 3, right? Over 3, up 1. Over 3, up 1, right? So that gets us to our 3 times our original vector here. All right. And then if you see V unit, right, that's talking about vector on our unit circle, trying to get it with a magnitude of 1 there, right, trying to get it with a magnitude of 1. All right, looking at, again, scalar multiplication and summative added together, you just follow order of operations. So do your multiplication first, then add them together. And this is a specific thing called our linear combination. All right. Finally, here we talked about dot products and all the different things associated with that. So again, dot products is multiplying the different components. So you multiply x by x and y by y, and then you add them together. And when you do a dot product, you should have one ending value. Okay, one ending value. Then we talked a lot about how we can calculate the dot product using our angle if we know it, or we can use this equation in a different form in order to figure out the angle between 2 vectors. All right, so we can do that. And then we talked about a special case. If the dot product is equal to 0, that means they're orthogonal. They're 90 degrees to each other. Okay, they're 90 degrees to each other. And then we talked about standard basic vectors, right? So again, either being 1, 0 or 0, 1 and writing them as E1 and E2. All right, so that any vector is a sum of the basic vectors here, right? Where those are the coordinates. Okay, so x and y are the coordinates of the vector. All right, so again, vector -6, 7 can be written as -7 E1 plus 6 E2. And if you really want, you can replace E1 and E2 with those coordinates, multiply out, and then add them together and see that, oh, this actually makes sense. All right, and again, the reason we do that is because it makes it easier when we have to deal with those trig identities where things can get pretty nasty pretty quickly. So again, it really helps with those guys there. All right. So that concludes 5.3 for us, okay? So you guys can do the checkup. Apologies. You can do the checkup on your own here. Again, the key for this is going to be having all of those equations next to you. All right. Again, it's not a complicated mathematical process. What's complicated is understanding which process you're being asked to use. Right. So if it says dot product, what equation are you going to use? If it's asking you for in terms of the standard basic units, right? What is that asking you to do? So having that next to you will be super helpful. All right. And you have one quiz here. So 5.3, again, that's what you should be working on tonight if you are up to speed. All right. And then obviously, once you are done with that tonight, again, part of your homework will be to finish up 5.4. All right, so this will go through, of course, reviewing all of the different lessons that we learned throughout. Okay, it'll give you a review of some of those calculator skills. And again, you've got extra credit practice, extra credit discussion, and then, of course, your mandatory CST. All right, so that's what you are being expected to work on. Right, and again, I know that this is potentially a lot of work here with your quiz and your CST, but you have an extra 30 minutes right now when I'm done talking, you guys are going to have that time to work on it. Okay, so by all means, we are 30 seconds away from being done with class. So, of course, if you've got questions, comments, concerns, reach out. But that's kind of my expectation, is that tonight you're finishing Unit 5 so that tomorrow we can start on Unit 6 here. All right, so again, please use this 30 minutes right now to work on stuff related to class. And again, of course, let me know if you have questions. But other than that, I'll see you guys tomorrow. Good luck. Let me know when you need me. Goodbye, goodbye.